Hi there. So isn't it wonderful seeing all these developers come together from around the world to talk about modern Android development? So it's a good time to ask ourselves how modern our testing practice might be. So of course, we don't like modernity for modernity's sake. We want to use modern practices because they help us to become better engineers. So a quick example, here's some code I might have written 5 or 10 years ago on Android, class with a single public method. It takes a string parameter, and in the body I call string.toUpperCase. Now, of course, if I passed in null, then the whole thing would blow up. But using the modern language, Kotlin prevents this mistake from happening. So what if there was some way that we could prevent common mistakes in testing? So how modern is our testing practice? Are we just testing like it's 1999? So I'm going to quickly try and answer that question by going through the history of testing on the JVM and related ecosystem. So in 1994, you had SUnit. SUnit is the grandparent of what are called the XUnit frameworks. So when you say XUnit, X is a wildcard. You substitute X with the name of the framework or the name of the language. So for example, NUnit for .NET, RUnit for Rust. And this was authored by Kent Beck, who is one of the advocates of extreme programming. So 1 year later, in 1995, we have Java 1.0 released to the public. And then in 1998, we get our own XUnit for Java, again by Kent Beck. So JUnit, we're going to use another framework later on, but if you think that means that I personally hate JUnit, then please just abuse yourself of that notion. I think JUnit is fantastic. I love its extensibility and its runners through rules and runners. And imagine writing a framework that lasts for more than 20 years. It's a fantastic achievement. Now, in 2001, we have the first dynamic mock object framework, which is called EasyMock. So let's have a look at how we might be testing in 2001. So this is some code that I got from the EasyMock website. You can see here we've got the essence of a dynamic mock object creation framework. So we can inspect the fields of the test and look for the mock annotation. And then without manually having to subclass or implement an interface, we get some test doubles on which we can stub or record a behavior for the case of our test. But if we look further at the code, there's some things that might strike us as unusual. So here we're telling the framework that we expect an interaction with the mock object. And that's because in the system under test, which is just the private method here, we're calling strings.clear. So we have to tell the framework what interactions we expect with the mock before they happen. Now, if I were to comment out the mock.clear line, then the test would actually fail. The other interesting thing there is we have to manually tell the mocks to do their work. So if we look at the first decade or so of testing on the JVM, it looks like this. We've got SUnit in 1994, Java 1 year later, and then JUnit in 1998, and EasyMock in 2001. So let's look at the next decade and see what advancements there has been in testing. So 2007 is quite a momentous year. We get Mockito, which is another dynamic mock object framework. And let's just have a look at some code to see how things have evolved. So we have the same ability to generate mocks, but we don't have to worry about informing the framework in advance about what interactions we expect with the mocks. And we don't have to tell the framework we don't have to tell the mocks to do their work. So altogether, that means a nice division into arrange, act, and assert, because we don't have to worry about informing the framework of interactions with the mock in advance. So 2007 if you were at Google at the time, you might have noticed one of these posters go up in the lavatory, and this is part of an initiative called Testing on the Toilet. So it's a bottom-up testing engineering initiative where a group of Googlers got together and wanted to disseminate knowledge around the company about the benefits of unit testing and best practices for unit testing. And some of those posters actually got turned into blogs on the Google testing blog. It's a really great read. You can see how testing has evolved over the years. Like some of our understanding of test doubles comes from this. And if you really want to go into detail, there's this excellent book, Software Engineering at Google, Lessons Learned for Programming Over Time, and that goes into the whole testing on the toilet initiative and how unit testing is done at Google. So if we summarize the second decade of testing on the JVM, we just have this one momentous year, 2007. Now, what about the next decade? Well, in 2016, we have Kotlin 1.0 released to the public. In 2019, Kotlin becomes the preferred language for Android development. So if I make a timeline out of that, it's actually quite sparse. There's no developments on testing in the timeline. And the reason for that is if you're anything like me, during this time, you're actually testing in the manner of the previous decade. So if I was to ask someone on the internet to roast my testing practice from this time, they might say, oh yeah, you're using JUnit from 1998 and a second generation mock object framework, which is Mockito, so nothing special. So to answer the question originally posed, no, we weren't testing like it was 1999, but we could have been testing like it was 2007. So what can we do to make things better? Well, for me, what opened my eyes was this presentation I saw by Ivan Towson at a Microsoft conference a number of years ago. So this is about property-based testing, and we're going to briefly explain what that is, look at how that can be used for testing an Android view model, and finally, we're going to look at how we can use JUnit to write property-based tests, even if we don't have access to a more modern testing framework. So the upcoming tests are going to be written using a testing framework called Kottest. If the name sounds a little unfamiliar, it's because it used to be called Kotlin test, but because of the namespace conflict, it got renamed to Kottest. So we're going to start with a very, very simple system under test. So this is just a simple function to calculate a maximum of a list of integers. So just to briefly talk through the code, we get the iterator of the list. If there's no elements, we return null because a maximum is a meaningless concept on an empty list. Then we get the next element as a max so far. And while there's still elements in the list, we update the local maximum if it's larger, and then finally return that in the end. And if you're getting deja vu, that's because this code is actually copy-pasted from Kotlin standard lib, and I've just given it an easy to recognize name, which is mymax. So let's write some typical unit tests using Kottest. So you might see this doesn't look too different from JUnit. Now that's because Kottest supports different testing specs or testing styles. And this one here is called annotation spec. We just use this @test annotation as metadata on the functions in the test class. So we're just saying, hey, we're telling the framework, hey, this is a test. So annotation spec is designed basically as an easy path of migration from JUnit. Now, we're writing tests against our mymax function. We start by throwing at it the list containing 4, 8, and 7, and the max should, of course, be 8. Then we can reverse the list and also assert that the max will be 8. And then finally account for the edge case of the empty list. So we're essentially taking inputs values as inputs and then comparing the outcome. Well, we're checking the output is what we want. Of course, if I run those tests, they'll pass, but tests are designed to protect us against bugs, protect us against faulty implementations. So how good a job do these tests do there? So Donald Knuth said that premature optimization is the root of all evil. So let's optimize this MyMax, and we're just going to return the second value in the list is our bad implementation. Second value in the list if there is one. And using the first the set of tests we wrote with value-based testing, the tests actually pass, which means they haven't done their job. They haven't protected us against a bad implementation. So this feels like the kind of problem that we could solve with a more modern technique, just as we solved null pointer exceptions at the start of the presentation. So let's start by just playing with the library here, Kottest, and seeing what we get with this artifact property, io.kotester property. So we get a nice function called checkall, and that sounds kind of promising. It sounds almost as if we want to check all lists of integers. So after the checkall, we get a block with access to this lambda parameter called ints. Let's just print out and see what happens. And you can see right there, we get a purple rain, if you will, of lists of integers, including some edge cases like the empty list and so on. So what we've done here is offload the burden of choosing test values to the framework. Now we can concentrate on writing something called a property, which is basically a rule that we expect the system under test to behave, to follow. So here's the first one. No elements greater than MyMax. So for whatever list of, well, first of all, we're not interested in the empty list for this particular test, so we just return early if we don't encounter that. Then we get the max, and then just assert that there shouldn't be any member of the list that's greater than MyMax. And then we can do something very, very similar for the case of the empty list. So you can see that there's only one value for empty lists. So you can think of property-based testing as almost like a superset of value-based testing. So now when we run the tests against our bad implementation where we just return the second element, they fail, which is what they're supposed to do. And they found a counterexample here. So you can see that it's found the list starting with 0, 1, -1, and so on. Of course, property-based testing isn't a magic bullet. You can still make a mistake. So if I were to switch to another bad implementation, so where I'm just going to return int.max value, those two properties wouldn't be enough to actually protect me from that. So I have to add another case, which is that MyMax should actually be in the collection itself. So that's a very, very simple example of property-based testing. Let's see if we can make it a little more idiomatic and learn something about how property-based testing works in Kottest. So here, you might be wondering how, well, first of all, let's have a look at the testing style of the spec. So here we've used string spec. So this means we write our tests we write our test names in quotations, and afterwards we write the test body inside a block. So a bit more idiomatic than the annotation spec we were using previously. Now you might be wondering how checkall got its list of integers, how checkall obtained those values. So under the hood, checkall and property-based testing and Kottest use generators called gen. So generators are the sources of the values. Now there's two subtypes of generator. There's one called an arb. Arb stands for arbitrary, which means random. It's when you have a an infinite set of values and you can only take a sample and some edge cases. So here I've made a generator called non-empty lists. It's just the default arbitrary generator for list of integers, and we filter out empty lists because we're not interested in that for this particular generator. The other type of generator is called exhaustive. Exhaustive is when you have a finite set of values where it's possible to enumerate or exhaust them. So here we have a generator that just returns one single value, which is the empty list. Now we can start writing our test, and we supply the generator as a parameter to check all. And just to show you some of the furniture in Kottest, I've used this function called withClue. So normally when we have a test failure, we try and look at the test name and look at the failure message or the exception and work out what went wrong. withClue just provides you an opportunity to supply a bit more context in the case of a failure to help the maintenance programmer work out what's go wrong. So when this test will fail, it'll actually print the message inside withClue. So to go on to some more property-based tests, the other properties, this time you can see we've used for all. Previously we used check all. So what's the difference? Check all has a return type of unit in the block that you write afterwards. So if you want to indicate a test failure with check all, you throw an exception. For all has a return type of Boolean, so you just write a Boolean expression there. And we've said whatever non-empty list, that list should contain the value mymax. And we can do the same very easily for the empty list. Now, if you want to have a play with that project, there's a link here, and I've put it in the notes on the talk website as well. So that might be very well. You might say, okay, that's very well. That's all very well. That might be good for testing something very, very simple, like a function to calculate a maximum. But how do we go about testing something larger, like a view model? So we're going to have a look at how we might test a view model using property-based testing, and we're just going to default to the Android architecture blueprint app because it should be familiar to us. So just have a look at the behavior here. You have active tasks, completed tasks, and then you can clear the tasks. Very, very simple. Very, very simple app for maintaining a to-do list, essentially. Now let's have a look at the existing JUnit test that we have inside the Android architecture blueprint sample. So you can see immediately we have these two rules, a rule for coroutines and a rule for the Android architecture components, the live data. And then we have some instantiation of the object graph. So this is some boilerplate. Let's just convert this boilerplate to Kottest first of all to get it out of the way, and then we'll look at some property-based tests. So here we're going to use funspec. So for funspec, which is the default, you write the tests as inner functions inside the init block. And we don't have rules in Kottest. So in JUnit, rules are essentially pieces of code that you might want to reuse for setup and teardown between different classes of tests. We have test listeners in Kottest, and let's just have a look at the one for coroutines. So we implement test listener, and then we get access to some lifecycle callbacks before spec and after spec. So these are equivalent of before class and after class. And within those, we just set the coroutines dispatcher to the test coroutine dispatcher that we can optionally supply in the constructor. And we can do something very, very similar for the live data for the Arch task test listener. So now we've got that boilerplate out of the way, we need some values in order to write property-based tests. We need our properties to apply over a set of values. So let's have a look at the existing JUnit tests for clues about what kind of values we can supply. So looking at the first test, we have load completed tasks from repository and load into view. So we set the filtering to completed tasks, force a load, and then we inspect if the data loading indicator is turned off, and we make sure that there's only 2 items on the screen. So obviously there's some dummy data, and we've just filtered out the active tasks. And there's a very, very similar test there for errors. So when we look at these tests and we're transforming them into property-based tests, we're looking at the arrange and act part of the test. We're not looking at the assert, because the assert is going to be a pseudo property. So what's happening in the arrange and act here? Well, we're invoking some member functions of the view model here. And then in this one, we're also manipulating a dependency for the view model, which is the task repository. So that can tell us that the range of values that we have to supply for property-based testing are the set of reasonable invocations of methods on the view model and its dependencies. So let's try and model that in Kotlin. So first of all, we're going to write a task context. It's just a simple wrapper class of the 2 objects that we need to manipulate in order to exercise the system under test. And then we're going to declare an action which has a name, and then essentially a block in which we get access to the 2 fields of task context. So to see how that works out, here's an example of a task action. So it's called load. We set the filtering to all tasks, and then we force a load. There's one for completed tasks, and there's one for error. So essentially what we've done here is take the arrange and act out of the pre-existing JUnit test and put that inside some values over which we can iterate. So now that we have our values, we can enumerate them here. We can just make a simple list. And then we use this .exhaustive extension function to change that into an exhaustive generator. So that's how we get our values for property-based testing for a view model. What do we do now? What kind of properties can we write? Well, have a look at the floating action bar on this video here. So you can see the floating action bar is only present when you have the filter set to all tasks. So how is that modeled in the existing JUnit test? Well, there's only one test for it, and this is actually typical of the result we get with value-based testing. We're testing the happy path, but we're not saying anything about the other paths. What happens when we set the filter to active and when we set the filter to completed. So just to be clear, I'm not ragging on this project. I think this project is fantastic. I'm just saying that this is a limitation of our value-based testing. Now, of course, we can go in and we can pedantically add the missing test cases, but we've added some more maintenance burden, and that might work for 2 different types of filter, but what if we have other types of filter? So it's not ideal. We can do something better with property-based testing. So we can just have this one test here. It's going to say for whatever set of actions I perform on the view model and the dependencies, then it should always be the case that the add button being visible is exactly equal to the filtering label being set to all. And that one property-based test covers the 3 cases that were absent earlier. So what's another property? Well, you can see when we have the filter set to all tasks, we have active tasks and then completed tasks. If we filter to active, of course, then we only have active on the screen and the completed tasks are ghosted. So we can actually model that using another property-based test. We can say whatever actions we perform on the view model and its dependencies, then it should never be the case that we have an active task on display and the filtering label is set to complete. And there's the opposite, the corollary is also true. We should never have a completed task when the filter is set to active. So that's not the only type of property we can write. We can also write properties that apply over time. So let's have a look at our setup test listener here, which is another part of the boilerplate we were converting earlier. So we've implemented test listener, and then we've used before each and after each. And then we've done the basic instantiation of the object graph there. Now what we're going to do is we're going to mock the observers. So recall that fragments and activities get their data from the view model by observing the live data. And we're going to do that here. We're going to use these mock observers to observe the live data and then remove them at the end so we don't get any kind of leakage. Now that we're doing that, we can actually use Mockito to capture the items that were admitted in the live data. This is a trick that Jamie Sanson actually taught me. He's a really good software engineer at TradeMe, and I'd encourage you to check out his talks. But this is just Mockito code to capture all the live data that was emitted through looking at those mock observers. Now that we've done that, we can write this assertion over time, this property that applies over time. So we can say that whatever set of actions we perform, we expect the data loading indicator to be on initially and then to turn off. So if we compare that to the existing JUnit test, you can see that we're achieving that by manually starting and stopping the dispatcher, which to me feels a little bit inelegant. And it also only applies to one particular property, one particular case. It doesn't apply over all the properties as the previous test did. So I'll include a link to that project for you to have a look at. And also I'll put it in the talk app. So finally, what if you have 100 different dependencies already and 1,000 different transitive dependencies, and you can't possibly use something new like Kottest? Well, it actually is possible to write property-based tests in JUnit 4, so you don't need any new libraries. So we're going to have a look at how we might do that. So if you're familiar with JUnit, you might know about test runners. So for example, the Roboelectric test runner. In JUnit 4, you get this test runner called theories. And theories are essentially properties. Now remember with Kottest, we had two types of generators. We had exhaustive and arbitrary. Data points are the equivalent of exhaustive generators. So data points means I'm going to supply some values for our test. So here we've just written some test data, a list, the empty list, a few edge cases, like a sample of some list of integers. So now that we have some data points, we can write tests that we annotate with this @theory annotation. And you can see the tests have a parameter, which is the list of integers, and the framework or the test runner is going to supply those ints using the data points that we mentioned earlier. Now this is pretty cool. In JUnit we get this concept of assumptions. So assumptions are like assertions. If an assertion fails, then your test will fail. If an assumption fails, then the test will discontinue without failing. So it's a soft failure. So we're using assumptions here to filter out the empty list. We're not interested in that for this particular case. Now we can just get my max and then iterate through the list we've been supplied and then make sure there's nothing greater in the list than my max. Now, if you remember JUnit, if you remember Kottest, then we also had arbitrary generators. And we can do something like that in JUnit as well. So here we've got this annotation on the parameter of the test where we've supplied a number of iterations, number of lists to supply, and then a seed for random number generator. So let's have a look at that. The random ints is a class we write ourselves with 2 fields, and it points to another class which is random int supplier. So random int supplier is going to be newed up by the test runner, and we just have to override a single method here, or single function, get value sources. So in get value sources, we get a handle on the signature of the test function, and we're going to, after getting that signature, obtain the instance of the random ints annotation. Now we've got that random ints annotation data, we can use the seed from that to new up a random number generator. And then we can very naively generate some random numbers and then limit it to the number of iterations that we supplied. Finally, we just have to map these in what's called a potential assignment. It's just a wrapper class for JUnit, and then convert it to a mutable list, just to conform with the methods, with the function signature there. So to summarize, we're not testing like it's 1999, but we could be testing like it's 2007. Property-based testing gives us the opportunity to sidestep a potential issue in a test, just like other modern frameworks and libraries help us avoid engineering errors. You can use property-based testing in Android to test your ViewModels. And even if you don't have access to modern testing frameworks, you can still use JUnit 4. So that's the end of the presentation. So I understand there's some opportunity for questions now, so please go ahead. Okay, so the first question is, I wonder if we combine this with more BDD style tests, given, for example, combining this with the spec framework. That's a great question. So I looked briefly at the spec framework and I wasn't able to find property-based testing there. I wonder if there's someone in the audience who knows more about that. But I think personally BDD is great. This is where you write given, when, then. But at the same time, I think properties scale in a way that BDD doesn't. So the way the example for me is when we're looking at the test of the floating action bar, we can make 3 tests with BDD, or we can make 1 property-based test. So to summarize, I think BDD is great. Properties are also great. Okay, no more questions. Thanks very much for listening, everybody.